Now we're going to make more examples. Let us just briefly recall what we said in the first part of this video lecture. We faced the challenge of making the same random variable have a new distribution. So we had, in this example, a random variable x that was a standard normal distribution. We kept the same random variable, that's the same function, from the sample space to the set of real numbers. We just changed the measure, the probability measure. It was this blackboard boldface p, and we changed it to obtain a new boldface p. And how do we do that? Well, we specified a Radon-Nikodym weight or Radon-Nikodym derivative so that we could specify a new measure from the old one. And we used that after evaluating the moment generating function. We found that this new variable indeed had the moment generating function of a normal with an average theta instead of 0. And then we discussed how do we get one probability measure from another probability measure simply by specifying a weight in terms of a observable, a function g that depends on a random variable x. And how is that? We just have to define, so that the new measure is a probability measure, we have to normalize, putting in the denominator the average of whatever is in the numerator. And that this is what in statistics is called biasing. So we bias by this factor g of x. And now, in the second part of this video lecture, we're going to explore the most common type of biasing, which is size biasing. Size biasing is where x is a non-negative variable. That's when we can talk about size. We don't allow for negative sizes, let's say. And then we take this function g, this factor g of x, to be simply x. So size biasing is when we bias by a factor x, a factor g of x, which is actually just x itself. And here's the first example. We have a probability space. On that probability space, we have a Poisson random variable. And now we make a size bias of this variable. What is the size bias? We take a factor x as the Radon-Nikodym derivative of the new measure that we are defining in this action. And we divide by the expectation of x. Well, we know from previous modules that the expectation of a Poisson variable is a mu. And this new measure, p, under this new measure, the distribution of x minus 1 is again a Poisson. So that means if we take a Poisson random variable and we do the size biasing, then what we get is the Poisson plus 1. And Poisson is the only distribution with this very nice property. Okay, so if we're sampling, we take many sets that we can sample from, and each set will have a Poisson number of whatever object comes inside them. Then if we sample one of these sets, but now biased by the number of points that they contain, then what we get has distribution Poisson plus 1. Well, of course, we can never get anything with 0, but what is not at all obvious is that if we subtract 1, we are back to Poisson. Our second example is when our random variable has distribution exponential of lambda, and we want to define a new probability distribution on the same space. We're going to replace the old probability by a new one, which will be boldface p. And well, by taking a factor y to bias the sampling in that sample space. This lambda here is just 1 over lambda. 1 over lambda is the expectation of y. And as the last example of size biasing is actually just revisiting an example from the first video lecture in this unit, where we tilted the distribution of when we roll a die. Let me go back to that example. So here's in the first video lecture of this unit when we're rolling a die. So these are the possible values that we would obtain. And this is a factor g, which I'm taking as n. Okay? N here is just g of n. So this is really just n is y, we can say. This is just taking g of x equal x. So this would be n by now divided by the expectation of x. And the expectation of x, we know what it is when we roll a die. The expectation is 7/2. So this is where this 27n came from. And let us continue discussing here. So we had 1, 2, 3. We're taking values on this set with the same probability, uniform on this set. And this was the distribution P. And now we define a new distribution, which is a boldface P, which is by defining its derivative, its Radon-Nikodym derivative with respect to blackboard boldface P, by saying this will be, well, x is the outcome of the die usually, but now divided by the expectation of x, and this is size biasing. And what does it mean to size bias when we roll a die? Well, when we simply roll a die and we observe what is the face that is facing upwards, then we're choosing one of the 6 faces with the same probability. But now, when we size biased, it means we're not choosing one of the 6 faces with the same probability. We're choosing one of these 21 dots that we have in the dice. We're choosing one of them with the same probability, and whichever one we choose, we're asking how many dots are there in that face. This would be the size biasing of the experiment of rolling a die. This is what happens if we go interview people downtown and we pick a person. Then we're not sampling uniformly from the population. We're biased by how often people actually go downtown. This observation will conclude this video lecture.